and to the launch of the Global Geologic Geohazards and Risk Network. Thanks so much for joining, and while you're, please stay muted while we get underway. Thanks especially to those in time zones for whom this isn't an ideal time. It can be very early or very late, or perhaps the middle of the night, depending on where you are, and that's true for some of our speakers as well. First, I will share some housekeeping. There is simultaneous translation available for this seminar. So you can use this QR code, or Kim, can you please put the link in the chat as well? Great, so you can go to that link, select the language of your choice, and receive either written or audio simultaneous translation. We'll keep people muted as we go through the speakers today and save questions for the end. Feel free to contribute in the chat as we go along, and we'll try to address the questions to the right people as we get to the end. Next, I'd like to introduce the team behind the network and this event. I am Malaika Almi, the Program Manager of the Natural Hazards and Climate Change Geoscience Program at the Geological Survey of Canada. And I am joined, and I'll invite them to come on screen and say hi, by John Schneider, Director of Schneider Geohazards and former Secretary General of the Global Earthquake Model Foundation, and Sahar Safai, founder of Sage on Earth Consulting, currently Disaster and Climate Resilience Solutions Director at Arcadis, formerly also of a variety of organizations many of you may be involved with, including the UN Office of Disaster Risk Reduction. I would also, John and Sahar, do you want to turn on your mics and just say hi so folks know who you are?
Good morning, good afternoon.
Greetings, everyone. Great to see you this morning, or not see you yet, but great to have a nice turnout for this first seminar of GeoRiskNet. Thanks.
Great. Sahar, do you want to say hi?
Can you? Okay, sorry, I guess I was partially on mute. Good morning, good afternoon. I am Sahar, and it's a pleasure to have such a great participation. Looking forward to this session. Thank you.
Great, thanks. I'd also like to acknowledge our task team who have served to guide us in kind of strategic directions and ideas as we get this network underway. So their names are online here, on screen here, and they come from a variety of organizations around the world, and they've been fundamental in kind of keeping us, helping us fill gaps that we've observed in this community. But with that, I will turn it over to John to share kind of information on the network and then introduce our first speaker.
Thank you, Malaika. So this is GeoRiskNet. This is the first seminar that we've had. We've just initiated this organization, so we thought it'd be appropriate to tell you a little bit about it. Many of you who are online have been interacting with us, but quite a number of others, for you, it's the first time. So I'm going to start with basics. What are geohazards? And I think it's relevant because this is even a debate within the community as to what should be included or what shouldn't. But generally, geohazards are geological phenomena that pose risks to human life, property, and the environment. Very basic definition. But the hazards include earthquakes, volcanic eruption, tsunami, and landslides, as well as sinkholes, avalanches, and ground subsidence, depending on your particular interest. So anything that's driven by geological processes, either deep within the earth, the tectonic, so-called tectonic forces, or more superficial processes, which are more local. Overall, geohazards are responsible for on the order of 10% of deaths and 25% of economic losses due to all natural hazards. But they also tend to represent the largest proportion of really large disasters. So 50% of deaths for those disasters that have unfortunately led to more than 100,000 deaths. Next slide, please, Malaika. So to put this further into context, geohazards really come together at what we call subduction zones, which are the places where tectonic plates come together, particularly oceanic plates and continental plates. The subducting plate to the right is heavier and more dense, and therefore sinks underneath the continent. But it also locks at the interface as the tectonic forces are driving these two tectonic plates together. So you periodically, so every 100 or so years, you might get a very, very large earthquake that breaks that interface. And in addition, as you move down dip from that interface, you have the melting of the upper surface of that plate, leading to volcanic eruptions. When an earthquake happens, it often triggers tsunamis, because the upper plate there is then flexed and affects the water column and drives potentially very large tsunamis that can cross an entire oceanic, cross an entire ocean, which we'll hear about today with the Kamchatka events. Obviously, landslides can also occur from ground shaking as well. So you had this confluence of all these processes leading to multiple hazards. And again, today's presentations will describe in detail how this came to pass in Kamchatka at the end of July last year. Next slide, please. So what are the gaps and challenges? Why did we, what is the driver behind GeoRiskNet? Just very briefly, we found there have been perhaps hundreds of people looking into this over time. But we found that there's generally poor access to information for geohazards in that broader context. Lots of information on individual hazards, but lots of gaps as well. Poor coordination internationally for developing understanding about risk assessment. Geohazards themselves tend to get left behind in a world that seems to be predominantly concerned with hazards that are driven by or affected by climate change. And there tends to be a disconnect between hazard risk assessment and what we call resilience decision making. That's really bringing the sort of end-to-end, the science through to the application together. So this is an area we'd like to focus on. There's no international organization that actually addresses geohazards or has direct responsibility for coordinating activities across the planet. Next slide. Just to give you a little bit of a flavor for the organizations that have been involved and are working with us, I'm focused here on international bodies, international networks. There are many organizations and individuals sitting behind these. So we have the Global Earthquake Model, the World Organization of Volcano Observatories through IAFSE, which is an organization of professionals that works with volcanic observatories around the world. The Global Tsunami Model and the World Community of Geological Surveys are all essentially networks of organizations. Then we have the World Bank Group, which runs the Understanding Risk program and brings in many professionals across the not only scientists and engineers, but also disaster managers. And at the UN level, UNESCO and UNDRR have been quite supportive. Next slide. So GeoRiskNet aims to facilitate collaboration, access to data sets and tools and expertise, promote capacity development, particularly in developing countries, advocate for geohazards within the broader community, promote and facilitate guidelines and information that can support multi-hazard risk assessment. If you want more information, we just put out a newsletter. We have a website, and obviously you can also email us to find out more. I would now like to introduce our first speaker on the Kamchatka earthquake. Zoe Yin, Dr. Zoe Yin is a PhD in geophysics and is an expert on geodetic observations of earthquakes or plates and studies large earthquakes, models their behavior and so forth. She's a Mendenhall PhD postdoctorate at doing postdoctoral studies at the U.S. Geological Survey in Golden, Colorado, and has just written a very interesting paper on the impact of the Kamchatka earthquake from the perspective of the USGS system. And I would like to now turn it over to Zoe to tell us about the earthquake. Thank you, Zoe.
Great, thanks for that introduction. Let me see if I can share. Can you see my screen okay?
We can, yeah. And that you're
Okay.
on the presentation, that looks great.
Okay, great, excellent. All right, thanks, John, for that introduction. And I'm really excited to talk to you today, like John said, about the USGS response to this magnitude 8.8 earthquake that we saw in July of last year. I'm a postdoc with the US Geological Survey, and the work that I'm going to talk about today is very much a collaboration between all the folks that you see listed here. And so I just want to mention that a lot of the work I'm going to show is going to be the work from these folks here. So I'll start with the big headline, which is that in July of last year, we got a new number 6 largest magnitude earthquake that we've instrumentally observed on our planet. And so earthquakes this large are rare, and it's rare that we get to observe them. So it's kind of exciting from a geophysics perspective to dive in and see what we can learn from this event about what's happening in these complex subduction zones. So I'd like to zoom into the region where this earthquake happened. So here we're sitting at the boundary between the Pacific plate and the North American plate, where, like John mentioned earlier, this Pacific oceanic plate here is subducting beneath the North American plate and generating large earthquakes. So we've seen 2 major earthquakes on this subduction zone. The first one was in 1952. We saw a magnitude around 9 event occur off the coast of the Kamchatka Peninsula here. This is the 5th largest instrumentally recorded earthquake. And then obviously in July of last year, we saw a magnitude 8.8 earthquake occur really close by, indicated by the red star for the 1952 event and the yellow star for the 2025 event. So what I'd like to do in this presentation is kind of take the lens of response, so take the lens of the USGS response to this event, and kind of go through all of the products that we produced to describe what we know scientifically about this event. So that includes the finite fault model, which is a description of the source of the earthquake and the slip at depth. The shaking, which is comes from the USGS shake map, which is informed also by felt reports called Did You Feel It reports. We can talk about estimations of ground failure from the USGS ground failure map, impacts from the pager alert product, which estimates economic losses and fatalities. And then hopefully at the end, we can bring it all together and talk about what do these products tell us about the earthquake and how does that impact our understanding of ongoing hazard in this region. So before we get started, a quick caveat is NEIC, so I don't think I said in the last slide, the NEIC is the National Earthquake Information Center, and we do 24/7 monitoring of global seismicity. And so the kind of philosophy around releasing products at the NEIC is that we release products as soon as data is available to support them. And then as more and better data becomes available, we release new versions of products. So for example, here we can see in the purple for our finite fault product, we start with a kind of a very smoothed version of the slip distribution. And then through time, as data becomes available, it becomes more detailed and changes a little bit. So I'll generally today be talking about the most recent products that we have available, but just know if you're looking at our event pages, if you're looking at our data products, they are going to evolve through time as more data becomes available. Okay, so I'll start with the slip distribution. So often as geophysicists, we want to know after an earthquake happens, what was the slip at depth on the fault that was driving that, that shaking, that seismicity. And so we use geophysical observations. In this case, we use teleseismic broadband data. We use INSAR data, which is a type of satellite remote sensing data that senses deformation at the Earth's surface. And then GNSS data or GPS data to show static offsets at the surface. So you can see we have 2 GPS stations or GNSS stations here that are close to the rupture. And so we use these observations to to solve for what slip is happening at depth. So you can see our slip inversion is shown here in these kind of white to purple colors. And these types of data products, these slip models are important both in response. So they're, for example, they can be used as the input to modeling the tsunami and also in long-term hazard calculations. So for example, we use these types of models to track the stress accumulation on subduction zones and locking. So in this case, for the Kamchatka event, we saw an inversion that showed about 190 seconds of slip duration, which is pretty typical for an earthquake of this magnitude. We saw a unilateral rupture to the southwest, which just means that the earthquake started here at the gray star, and then slowly through that 190 seconds moved to the southwest. And we actually saw the largest patches of slip here at the farthest southwest end of the rupture that were kind of strongly constrained by this GNSS station SKUR here to the southwest. Next, the shaking distribution. So this is primarily distributed through a product we call the shake map. So that's what you can see here. And it's using a rupture plane. So in this case, these black squares are indicating the extent of slip based on the slip model that we looked at in the last slide. And we're using that to predict the shaking distribution throughout the region. So these colors are indicating our estimates of what shaking should be. And these are typically constrained by any observations that we have available. So in this case, this is a sparsely populated region and a region that it's difficult to get data from. So we had about 120 did you feel it reports. So these are reports that people who experience the shaking can submit, and they can be mapped to approximate intensities. So we had about 120 of those reports that are constraining the field of shaking. And then we also have some really limited regional strong ground motion data. So we have strong ground motion stations that are collected by the Kamchatka Regional Seismological Center. And you can see here, they're just reported as peak intensities as modified Mercalli intensity MMIs that are then used to constrain the shake map. Okay, so we have a product that we also use called the ground failure product to estimate landslide extent and severity. So this combines the estimated shaking from the shake map with some kind of landslide susceptibility model to estimate the number and the extent of landslides. So for this earthquake, we reached a red alert level. So we expected over 260 square kilometers of exposure to landsliding. And actually, a couple of folks, Alex Grant and Elaine Collins here at the USGS, did a really cool study looking at Sentinel-2. So this is satellite optical imagery. And they used that optical imagery to map landslides along the coastline of this Kamchatka Peninsula. And they mapped at least 346 landslides over this region. And so far, the comparison between these two things suggests that our landslide model probably overestimated the number and extent of landslides a little bit. And that's probably because the model, the data that our landslide model is trained on fewer subduction type earthquakes. And so that's something that they're looking at improving in the future. Just for a kind of a ballpark comparison, so far it looks like the number of landslides mapped for this earthquake are pretty similar to those mapped for the 2011 Tohoku, Japan subduction earthquake. Damage and losses. So we use PAGER, the Prompt Assessment for Global Earthquakes for Response product, which again combines those estimates of shaking from the shake map with information about population density and regional construction practices to estimate fatalities and economic losses. So we estimated 10 to 100 fatalities and more than $10 billion in damage for this event. So that's a yellow alert for estimated fatalities, a red alert for economic losses. And when we compare that to what we kind of observed from reported damage, there was only one indirect death reported in Japan from the tsunami evacuation, which I'm sure others will talk about. But most of the damage was reported in a city of Severokurilsk, which is on one of the northernmost Kuril Islands. And it was really extensive damage there. There was reports of almost all the buildings having damage and a tsunami that destroyed a fish processing plant there. So you can kind of see from the discrepancy here between the PAGER estimates and the reported damage that the PAGER product likely overestimated the true fatalities and economic losses from this event. So there's two possible reasons that this could be. One is just the uncertainty in the true shaking exposure because there is just limited data availability and nearby instrumentation in this region. The second one's kind of interesting, and it's that after the Kamchatka Peninsula endured the 1952 event, there was a lot of rebuilding that happened, particularly in Severokurilsk, which actually was completely destroyed in the 1952 event and had to move further inland and was presumably built to a more modern standard and with kind of earthquakes front of mind. And so because PAGER uses past events to calibrate losses, they don't consider those potential improvements in the building standards that may have happened as a result of past earthquakes, but it should, if there were to be another event here, would do a better job kind of estimating these losses. Okay, so that's all the data products that I'm going to talk about for now. I'd like to spend just a couple of minutes talking about what these information products imply for the seismic tectonics, for the ongoing hazard in the region. So one kind of big picture way that we often think about subduction zones as geophysicists is that these major megathrust events will release most of the accumulated stress and must be kind of reloaded by the subducting of the slab in order to produce another great earthquake. I mean, it's a very rough heuristic, but it's one that I think that often is a mental model for geophysicists. So we can do a quick back of the envelope calculation and say if there were 8 millimeters per year of convergence over the 73 years since 1952, we would expect no more than 6 meters of slip deficit to be accrued if the complete was completely locked the whole time. Yet we see in our slip model that we expect regions with over 30 meters of slip. So there's kind of a discrepancy there. One reason that this could be is that maybe this event was rupturing different parts of the fault than were rupturing in the 1952 earthquake. So to look at that, we could look at the overlap between the 1952 event and the 2025 event. So here's just a little bit of an animation with the 1952 event shown in gray to white on the back with high slip indicated by darker colors. And then overlaid on it are contours of our latest slip model. And you can see there's actually quite strong overlap between these two slip distributions. So, you know, there's a lot of caveats here. Our slip inversions are relatively insensitive to slip at the trench, and they're relatively insensitive to small scale variations. But there's certainly a lot of similarities between these two events. So together, this kind of shows that these megathrust events can happen on the same sections of a subduction zone more often than we may have previously believed, which obviously has big implications for hazard and risk. Okay, so takeaways. The 2025 event was a relatively shallow unilateral rupture, which included large peak slip to the southwest. Damage from the shaking was limited by the sparse nearby population in the region. The 2025 rupture has many similarities to the 1952 rupture, but it's not totally clear yet whether it's re-rupturing the same parts of the fault or not. And finally, megathrust events can happen on the same sections of a subduction zone more often than we may have previously believed. So with that, I'll just plug, we have a paper that John mentioned that was just published in the Seismic Record, and it's open access if anyone wants to take a look at it for more details. And hopefully we'll have some time to discuss at the end. So thanks so much.
Thank you, Zoe. That was wonderful and a great overview and thought-provoking there. So yeah, we will save questions for the end, but I invite you to look in the chat. You've already got some questions coming. So thanks so much. That was great. Next, I'll invite Dr. Fabrizio Romano to, Fabrizio, you can start sharing your slides while I introduce you, if you would like. Dr. Fabrizio Romano is a senior researcher at the Istituto Nazionale di Geofisica e Vulcanologia, in Italy, and a member of the Global Tsunami Model. His research is focused on the rupture processes of tsunamigenic earthquakes, particularly through tsunami numerical modeling and the inversion of geophysical data. And his work also extends to tsunami hazards and warning systems, and he's one of the co-founders of the Italian Tsunami Warning Center. With that, Fabrizio, right now we're seeing your conclusion slide.
Okay.
Great, I will pass it over to you. Thank you very much.
Now, can you see? Because I don't know
Yes.
if you...
Looks
Okay.
great. Yeah.
Good. Thanks, Malaika. No worries for the pronunciation of Italian name of my institute. It's a pleasure for me to be here, and thanks for inviting me. And good evening or good morning to everyone, depending on your local time. So I'm going to present a recent study that I did with my colleagues from INGV and other institutes about the 2025 Kamchatka tsunami, and some features about the tsunami that can be explained by the complex seismic rupture. A short introduction, sorry for this repetition. Zoe already explained very well the mechanism of tsunamigenic earthquakes, but the same, allow me to repeat, the subduction zones in the world are the ones that host most of the seismicity at the global level and host the large seismic events, also the mega events. In particular, for example, the Sumatra 2004 was a magnitude 9.2, and this kind of events, if occur in the sea or close to the sea, has the potential to generate a tsunami that can propagate it also over the ocean at transoceanic distance. Here there is a simulation showing the 9.2 Sumatran Andaman earthquakes. Of course, if the tsunami is big, can have very, very dangerous impact with a lot of fatalities, people missing, at the capacity to destroy buildings, to damage the ports, and also nuclear power plant, like all of you for sure remember in 2011 for the Fukushima accident. Now, the 2025 Great Kamchatka earthquake was an earthquake occurring last July with a magnitude 8.8, the equivalent in terms of seismic energy of more or less 15,000 Hiroshima bombs, just to have an idea of the energy that this earthquake can generate. It was due to the mechanism, subduction mechanism, where the Pacific plate subducts beneath the Okhotsk microplate, and the earthquake occurred along the subduction interface between these two plates. And this is the sixth largest event occurred since the beginning of the instrumental era. And the tsunami that was generated by this earthquake was a tsunami that traveled all over the Pacific Ocean. Here there is a movie, and this is the propagation of the maximum wave weight modeled by NOAA, that after 21 hours more or less reached the Chilean coast on the other side of the ocean with respect to the origin area. This tsunami was important, and it was followed by the earthquake was followed by a timely tsunami warning message issued after a few minutes by the Pacific Tsunami Warning Center. We can say that the warning from Pacific Tsunami Center was fast and efficient, and it was timely sent to the 46 countries around the Pacific Ocean. But while the tsunami message warning was issued very fast, we observed while the time was passing that the tsunami generated by this event was overestimated, fortunately I would say, with respect to the tsunami forecast produced by the warning system. Here there is to the left panel a figure showing the forecasting from the Pacific for the ocean, Pacific Ocean. In the middle, the same, but produced by the Japan Meteorological Agency. And to the right there is an histogram showing how the amplitude forecasted by these systems are with respect to the observations that we measured, for example, at the coastal tide gauges, and we can see that the observed ones are generally smaller with respect to the warnings issued. So, motivated by try to understand this discrepancy, we studied this earthquake by using a different kind of observations. First of all, tsunami observations from dart buoys that recorded the tsunami very well deep sea in the Pacific Ocean, and from the tsunami measured by the SWOT satellite that measured the sea surface 8 in the Pacific. I have to say that this second measurement is valuable for infer information from the tsunami genesis process, and this is a not so common observation when a tsunami occurs, because we have to find the combination of time and the dimension of the size of this the tsunami event, because the satellite have to pass exactly when the tsunami waves is passing in the ocean. So we were lucky in this sense, and we also used cosmic deformation observations from the Sentinel-1 satellite INSAR data for both the ascendant and descendant component in line of sight, and two geodetic cosmic offset from the GNSS network for stations located in Kamchatka. Then we inverted a multiple data set combining tsunami and geodetic data that is important for tsunamigenic earthquakes, because these two different kind of data, tsunami and geodetic, are complementary, because the tsunami data are able to resolve very well the features of the tsunami source in the sea, and the geodetic data are very well to reproduce the rupture information, the rupture features for the part of the rupture that is close to the land. Here we parameterize the fault surface through the SLAB2 models from USGS with quadrilateral element of 25 by 25 kilometers. And we compute a geodetic Green's function by using the analytical formulation by Nico and Walters. We use the same approach to compute the initial condition for the tsunami, and to propagate the tsunami, we use the Jacques model that takes into account the dispersive behavior of the tsunami waves. And we did this on a bathymetric model with a spatial resolution of 1 arc mean. After generating the tsunami Green's function, we perform a joint inversion using an global optimization method that is the simulated annealing, exploiting the linear combination approach of this Green's function. And we invert this data for estimate the slip model, that is the slip, the dislocation, and the rake angle of the dislocation. We use as a priori information a rupture velocity along the fault of about 2 kilometers per second that we took from the USGS finite fault model that Zoe showed before. And we found an average slip model from the entire ensemble of the Explored 1 by the inversion that we prefer with respect to the best one, because we want to avoid any possible outliers in the models that correspond to the minimum, to the global of the cost function. This is the model that we found after the inversion, that is characterized consistently with the USGS model by a unilateral rupture propagating from the epicenter in southwest direction. We individuate three main asperities, one that is a moderate slip close to the epicenter, and the other two that are in the middle and to the south of the fault surface with the peak slip of about 17-18 meters. And the rake is consistent with the convergence direction of the relative between the two plates. For what concern the comparison between the observed data and the modeled one, this model predict very well both the tsunami and geodetic data, as you can see in these figures. And I want to focus on the SWOT modeling, where we are able to reproduce with the JACURS code also the dispersive behavior of the tsunami propagation in the open ocean. Now we focused on two things. First, the comparison of the rupture model of the 2025 event with respect to the 1952 one. And we observed that the 1952 with the 2025 is in a sense complementary, or they are also very similar. In particular, the first model of the 1952 obtained by far-field tide gauges suggests that these two ruptures are complementary. With the 2025 that cover the shallowest part of the subduction, and the 1952 the deeper one. But a revised model of the 1952 used the sediments data in the near field of the tsunami suggests a possible different mechanism, different pattern of the rupture, and in this second case the two ruptures are almost overlapped. Remain some uncertainties with respect of this comparison, but we can the same state that the 1952 the time passed from the 1952 is able to recover the interseismic coupling that and generate a possible harder earthquake like like occurred for the 2025. The second aspect that we investigated with this study is as I said at the beginning, the limited impact of the tsunami associated to this earthquake, and we can divide it into this impact in the far field and in the near field. In particular, in the far field, the impact was smaller with respect to the one occurred in the 1952. This is due probably to the limited shallow slip that occurred in this earthquake, and that can be translated in a smaller tsunami potential energy that we computed by considering the initial water displacement, that is from 5 to 10 times smaller than the 1952. For what concerns the near field impact, on the other hand, we can say that the impact, if we consider the maximum run-up measured by this earthquake, is similar to the 1952 event. This is due probably to a trade-off between the smaller potential energy associated to the 2025 event, but at the same time a shallower rupture with respect to the 1952. And in the combination of the trade-off between these two ingredients make the run-up comparable, about 15-20 meters. To conclude, I want just to highlight a couple of points. We estimated that the rupture process or the tsunami source for the 2025 Kamchatka earthquake, and we individuated a tsunami source that can be interpreted as a partial rupture of the subduction interface with an overlapping probably with the 1952 events. We found that there is a limited impact of the tsunami in the far field due to the shallow rupture of the source, and a comparable impact in the near field. But this is the first Pacific-wide activation for the Pacific Tsunami Warning Center after the Japan tsunami in 2011, and demonstrated the system that it worked very well, even if the forecasting was overestimated. I would highlight that this is a conservative choice, what we observed in this case, that saves life for sure. But the risk here is that there can be an overreaction when you have a very big conservative situation. How we can deal with this kind of problem? For sure, by reducing or better quantify the uncertainty, that can be due, for example, by using new sensors, or by introducing information resulting from, for example, data inversion. And last but not least, I want to highlight the fact that such a kind of study, in particular the rupture process, is important, is crucial to inform the seismic model when we are dealing with the probabilistic tsunami hazard assessment, like which we want to do in the Global Tsunami Model. Thank you.
Thank you so much, Fabrizio. Similarly, you already have questions in the chat. That was a great follow-on, I think, too, from Zoe's presentation. We will have other questions at the end. For now, I invite Ben Andrews to start sharing his screen while I introduce him. So thank you, Ben, for joining us. Dr. Ben Andrews is the director of the Global Volcanism Program with the Department of Mineral Sciences at the National Museum of Natural History of the Smithsonian Institution, and the leader of the IAVC Commission on Volcanic Hazards and Risks as of very recently. His research covers volcanic processes and hazards ranging from magmatic storage and recharge conditions through eruption to deposition, rates of mass, momentum, and energy transfer in different volcanic and geologic processes, analog modeling, optical flow, velocimetry, turbulence analysis, sample grain size and component analysis, experimental petrology, electron microscopy, and crystal isotope stratigraphy. Ben, please take it away. Thank you very much for being here.
Hey, thank you very much. Just real quick, can everyone see my screen? Okay.
Yeah, it looks great.
Very good. And my apologies for the second paragraph of that introduction. That was a lot of unnecessary information. Well, thank you all for having me here today, and I'll be speaking about some of the volcanic activity that occurred right before and then after the large earthquake that happened in Kamchatka just about, I guess, 6 months ago. So, as it says here, this is Kamchatka eruptions following the 29 July magnitude 8.8 earthquake, and the picture there on the left is of Krashenikov erupting for the first time in about 500 years, and that picture is from August 3rd, so 3 days or 2.5 days after the big earthquake. So for a little background, Kamchatka is often called, or sometimes called, a land of volcanoes. And in the peninsula there's 46 different volcanoes with Holocene eruptions. And this is a huge number of volcanoes. And some of those are large caldera systems. Some of those are, there's a couple volcanic fields, and then there's stratocones, such as we'll be seeing the activity from today. In any given year, about 2 to 4 of these volcanoes erupt. Of course, during this last year, it was, I think, more like 7 erupted. And as of this talk that I'm giving right now, there's 3 volcanoes currently erupting in Kamchatka. So indeed, it is a very active place. And some of the world's most active volcanoes are here in Kamchatka. As the example here, Sheveluch in the northern end of the peninsula has had 22 VEI5 or larger eruptions. Now, for the folks on the call that don't know what a VEI5 eruption is, which is totally reasonable, that's an eruption about the same size as Mount St. Helens in 1980. And so globally, an eruption of that size occurs on the order of about 1 every 10 years. And in the Holocene, we have 22 of these eruptions documented just from Sheveluch. So this is a lot of large eruptions from a single volcano. This area is monitored primarily by 2 agencies. There's the Kamchatka Volcanic Eruption Response Team, or KVERT, which is based out of Petropavlovsk-Kamchatsky, which is the major city in Kamchatka, down here in the southern end of the peninsula. And then we also have the Tokyo Volcanic Ash Advisory Center. And these 2 agencies use different or complementary ways of monitoring. So KVERT monitors using for the most part, ground-based observations, so seismology and cameras and scientists on the ground. The scientists from KVERT and also from, but more broadly, Russia have over the years put together amazing eruption histories for all these volcanoes using tephrochronology, so that even though Kamchatka is a very remote place, we have a wonderful record of its eruptions. That's why we can say Sheveluch has had 22 VEI5 eruptions in the last 10,000 years. The Tokyo Volcanic Ash Advisory Center, on the other hand, is one of 9 VAACs around the world, and it has jurisdiction over or responsibility for monitoring the volcanic activity in Japan and Kamchatka and Indonesia, and it does this using satellite observations. And so its mandate is that as soon as a volcano erupts, it needs to get an observation of that ash, and then a forecast where that ash is going to be so that airplanes can get out of the way. And as we'll see in the talk here, the principal hazard from the Kamchatka volcanoes and the principal hazard that occurred this last summer was ash and its threat upon aviation. And as a quick reminder, volcanic ash is not like wildfire ash or fireplace ash. That is to say, volcanic ash is not burned up stuff. It's not burned up organic matter. Instead, volcanic ash is little tiny rock particles. So little frozen bits of volcanic melt, frozen volcanic crystals, very small particles that if an airplane encounters enough of them, it tends to shoot down an airplane. And so as a result, the global community tries to make sure that airplanes know where volcanoes or where volcanic ash is so that airplanes can get out of the way. And this is an example showing some of that. So although Kamchatka is a rather remote place, a huge amount of air traffic goes very near to the Kamchatka Peninsula. So this is the schematic map of the air routes over the North Pacific that Tina Neal and co-authors put together about 15 or 18 years ago. And we can see that there's numerous major air routes. Pretty much all North Pacific air traffic goes just to the east of Kamchatka, and the prevailing wind directions tend to blow any ash from a Kamchatkan eruption into those air routes, or in the direction of those air routes. And so it's a very important place for monitoring where the ash is going to go. All right, to set the stage for the late July earthquake. Before this earthquake happened, there were 4 volcanoes erupting, starting from the north and moving south. Sheveluch had been erupting since, well, the last about 25 years ago, so since 15 August 1999. Klyuchevskoy had been erupting since April of 2025. Bezimiany had been erupting since the end of 2024, and Krimsky had been erupting also since April 2025. And because of these eruptions, the Tokyo VAC had issued numerous volcanic ash advisories, or VAAs. So we'll see an example of one of those in a minute. And then on 29 July at about 11:30 in the evening, there was a magnitude 8.8 earthquake, and activity at Klyuchevskoy increased. Now, I want to note, though, that there's some some confusion sometimes about whether the earthquake triggered activity at Klyuchevskoy or intensified activity at Klyuchevskoy, or what was going on. And this is important because at 2350, so about 26 minutes after the large earthquake, there was an ash plume that was extending 50 kilometers to the east of Klyuchevskoy. But this eruption, the explosion that was generating that ash plume had almost certainly begun before the large earthquake. And then at 00:36 in the morning on 30 July, so about an hour after the earthquake, there was a lava flow advancing down the southwest flank of Klyuchevskoy. So the earthquake had happened and the eruption was happening. The eruption had been going on beforehand, but activity at the eruption intensified at the same time as the earthquake, but very likely intensified right before the earthquake. So there's trying to unravel what triggered, whether this eruption was triggered by the earthquake is a little bit fraught, or takes more information. Now, this is an example of one of these volcanic ash advisories that the Tokyo VAC issued. This is for Klyuchevskoy for August 1st of 2025. And you can see in the upper left panel, the little red symbol is the volcano, and then that black polygon is the 50-kilometer ash plume, and then, or 150-kilometer ash plume. And then we can see that this is now extending. There's a forecast in the upper right panel for 4 hours later, and then another 6 hours later, and then another forecast in the lower left panel for 12 hours after that initial observation. And so this is how the volcanic ash advisory centers disseminate the information about these ash plumes. There are scientists at those agencies, at the Tokyo VAC and other VACs, who identify the ash cloud in satellite imagery, draw a polygon around it, and then publish that and send it out so that airplanes can get out of the way. All right, so that was the earthquake had happened, and Klyuchevskoy continued to erupt, and then about 2.5 days or 3.5 days afterwards, Krasheninnikov erupted at 4:50 in the afternoon, 1650 hours, and this was the first eruption of this volcano since the year 1550. So the first eruption of Krasheninnikov in almost 500 years. Now, there's one of the things I was supposed to talk about today was, were there problems with communication, or how were things communicated? And this is at the Global Volcanism Program, we received calls from the press about whether the most recent eruption had happened in 1550 or if it had happened in 1350. And I will be honest and say that whether it had happened in 1550 or 1350 doesn't really matter. If in the case of this eruption response, or in the case of the eruption, the volcano is erupting right now. It doesn't matter if it last erupted 500 years ago or 650 years ago. And this all had to do with confusion about whether the date was reported as a carbon-14 corrected date or an uncalibrated date or a calendar age. And so we were reporting it as one date, and scientists in Kamchatka, who we had gotten the date from, had reported as the other date. It was the same date. So this was some confusion that we had to deal with, and the scientists in Kamchatka also had to deal with. Now, at about 5 hours after that initial eruption, there was a 5 to 6 kilometer tall ash plume that extended 700 or 75 kilometers to the east, and there was ashfall reported in the park nearby. And we'll see a picture of that in a moment, or a map of the park. And the eruption intensity further increased the next day, so that there is now an 8 to 10 kilometer tall plume, which extended 185 kilometers to the east. And for reference, 8 to 10 kilometers is just about exactly the altitude that airplanes are flying at. So this is causing a potential. This could have caused a potential problem. Now, this is a map of the park right here. We have the inset map shows Kamchatka. That red outlined region there is the Kronotsky Nature Preserve, or the Forbidden Zone, as it says here. And within this, there's very few people living there. And so as a result, there is very little hazard or very little infrastructure damage, very little damage and threat happening to people on the ground, because there are very few people that live there. There were enough people, however, to report some ashfall happening in this park, in this restricted area. And this is the VAA that Tokyo sent out for that plume. We can see again this black polygon showing the ash dispersal almost due east from Klyuchevskoy, and then how that ash is expected to be distributed by the atmosphere, by winds in the stratosphere as it moves along. And here's some photos of it. The ash column there on 3 August rising up very dramatically. The top of the mountain is just below it's probably at about the height of that yellow label that says 3 August Artem Shelder from the Associated Press photographer or credit. And then this eruption transitioned to creating strombolian activity, which is to say lava fountains that we see on the right-hand side that then fed lava flows. And we see that lava flow pouring down the flank of the volcano there. If we look at the volcano afterwards, we can see the photo on the left shows from about a year before the eruption and the earthquake eruption. And then on the photo on the right, we see the aftermath of the eruption. We can see there's these 2 lava flows extending to the sort of north or the east-northeast of that northern crater. During the course of this, most of the hazard was being communicated by the CAVERT staff through VONAs, or Volcano Observatory Notices to Aviation, and then by the Tokyo VAC using volcanic ash advisories. During this time, so even though the only 2 volcanoes that supposedly erupted in response to the earthquake were Klyuchevskoy and Klyuchevskoy, there were other volcanoes erupting in Kamchatka. And so that's important here, that Kamchatka has a lot of volcanoes and lots of them were erupting. So Sheveluch, from about the time of the earthquake for the next 4 months, they issued 90 volcanic ash advisories. Klyuchevskoy issued 158 in the 2.5 months from 1 August to 20 October. And this VAA diagram here is from August 5th. Bezimiami, there were 22 issued. Klyuchevskoy, on the same August 5th that they issued a Klyuchevskoy VAA, Tokyo issued a Klyuchevskoy VAA right here. And then Krimsky had numerous VAAs issued as well. And just to illustrate again how much is going on, this is a satellite map that NASA made using their sulfur dioxide imaging products. And you can see from the Tropomi image here, you can see that there are at least 4 different SO2 sources, so 4 active eruptions going on at the same time on August 5th. So there's a lot going on that was happening with these volcanic eruptions. All right, so to sum this all up, there were 4 volcanoes erupting prior to the earthquake. Eruption activity at Klyuchevskoy intensified after the earthquake, or possibly moments before the earthquake. The eruption at Klyuchevskoy began shortly after the earthquake, about 2.5 days, and it had ash plumes that continued into November. So the earthquake happens, the tsunami happens, this eruptive activity continued for many months afterwards, and it has lava flows that are still active as we speak. The primary volcanic hazard from this activity was ash and its threat upon aviation, and that's because there's relatively minor hazard presented to the small local populations that are on the ground. And all this information was communicated by CAVERT issuing VONAs, or Volcano Observatory Notices for Aviation, and the Tokyo VAC issuing volcanic ash advisories. And so to wrap that up, here's a nice picture of Klyuchevskoy from a couple days after the eruption. And thank you very much.
Wonderful. Thank you so much, Ben. I am going to introduce our next speaker, Dr. Aletta Rizzo. She's the Geologic Hazards Program Coordinator at the Oregon Department of Emergency Management. Her work over the last 2 decades has focused on disaster risk reduction, community resilience, and the integration of human systems research into public policy and emergency management. Now, I know why Malaika asked me to introduce her. These are topics very close to my heart and my work. Please go ahead, Dr. Rizzo. We can see your screen.
Yeah, Althea, I don't know if you've unmuted yourself. We can't hear you. I know Althea was.
You know, at some point we should probably learn how to turn the mute button off. Okay, so thank you again for this opportunity to come talk to you about the Kamchatka tsunami that happened this last summer. Go ahead to the next slide. So when we are looking at our response to a tsunami like this, there's a lot of things that feed into our response. And the USGS has sort of a handy primer here of a lot of the things and the types of information that we look for during a response. You know, the first one is where did this happen and how big is it was? And then we're looking at you know, how many people may have felt it. Now, this information comes in over time afterwards, but this is the kind of thing that we're looking for. How big is big and where did it happen? So it happened in Kamchatka, which is a very long ways away from where Oregon is, so that we knew that when this happened, there would be hours before any arrival at the Oregon coast. In 2011, it was between 9 and 10 hours from Japan. So we were expecting this to take a little bit longer than that. Some of the other things that we factor into our response is, you know, who's living in the hazard area and who may need to be informed that there is a tsunami possibly happening. And then we factor into, you know, how big is the tsunami possibly, when's it going to arrive, what kind, what's the tidal, where is it, high tide, low tide? Is it during a storm so that we might have a storm surge on top of a tsunami surge? So there's a lot of different factors that we have to kind of pull together really quickly when one of these events happen, because this information goes out to all of our collaborating partners at the same time. So when the earthquake happens, our partners are getting the information that the earthquake happens. When a tsunami product like a alert, a warning, watch, or an advisory is sent out, a lot of our partners are getting that information at the same time. So at OEM, we're trying to pull all of these different pieces of information together because we know that people are going to be asking us about it very, very soon. So next slide, please. So when we're looking at the day, it happened at about 4:20 our time. And this is around when a lot of our folks are leaving for the day. So the timing was fortuitous in that a lot of our folks were still there, but some of our folks had already left, myself included. And there was a tsunami watch that was issued a little bit after 5 o'clock. And at 5:30, I was called back into the office to start response. And so when I came in, you know, I started looking at the tide gauges. I looked at what the weather's doing over there. It was, you know, during a summer day, so we knew that the likelihood of the transient population, our visitors to the coast, those numbers would be higher. And when we have our first coordination call, this is our Emergency Coordination Center sends out information that we're going to have a coordination call. And this is where all of our local emergency managers, our first responders, all of the people who are involved in our emergency support functions like communications, fuel, power, mass care, they all call in so that we're sharing the information with everybody at the same time. And then around 6:30, we changed from a watch to an advisory. So when we're in a watch situation, this kind of means we don't really know if a tsunami is going to reach us or not. And this is sort of our get ready period. When we heard that it was going to be an advisory, this means that we need to start taking action. When the Tsunami Warning Center up in Palmer, Alaska, sends out these advisories, that means the tsunami is going to be up to a meter high. If it was going to be over a meter, we would have gotten a warning. An advisory generally means we're not going to have inundation on land, but we're going to see strong currents in bays and harbors. So it's really important to get people off their boats, get people off the beaches, and get them out of the ports and harbors. Now, there was at least 10 hours before it was going to arrive in Oregon. So some of our fisheries folk did decide to take their boats out to a safe depth. And when it kicks into an advisory, that means that we're looking at doing some evacuation. And our local partners, whether they're the counties on the coast or the state police or the state parks, they are sort of in control of what happens locally in their jurisdictions. So I can't tell them to evacuate. That is a local decision. We had another state coordination call at 7 o'clock. And we held those kinds of coordination calls throughout the evening. And between our coordination calls that OEM was having with folks in Oregon, the National Tsunami Warning Center was also having coordination calls to share the most recent information about the tsunami, what kind of observed heights have we been seeing, any updates to wave arrival time or updates to expected amplitudes. Those first waves arrived about 11:30 at night, and this was rather fortunate because there weren't a lot of people on the beaches that would have been affected by this. And so we saw waves about 1 to 2 feet high. So it was not terribly impactful, but we did see very strong currents in our bays and harbors. And just to the south of us, California, you can kind of see that one finger of red energy hitting the coast. That was California. And they had a much bigger effect from this. And so they have far more people that they have to evacuate. And so, we were watching a lot of what they were doing and sharing as much information as possible as things came through. So next slide. So when we were looking at this response during this event, there's a whole bunch of different ways that we can share information. First of all, we have the NOAA National Weather Service coordination calls. For us, we turn to the National Tsunami Warning Center in Palmer, Alaska. Folks who are in the Pacific and South Pacific look to the Pacific Tsunami Warning Center. And so they have these coordination calls about once an hour or whenever they're expecting big updates of information. We have those coordination calls. But the Weather Service also has a Slack channel that they share information on. They have one Slack channel that's a little bit more open, and some of the public can reach into that Slack channel. But they also have a Slack channel that's just for emergency managers and responders. And that was a really efficient way to share information. In the past, we've done teleconferences, mass calls in on the telephone. Luckily with technology today, we can use Teams meetings and have shared graphical information, not just, numbered data. Another way that we were sharing information, and this was internal to OEM and to our cooperating partners, is there's the Homeland Security Information Network, or what we call HISN rooms. And this is another way for us to provide information quickly during the event. We had a number of the emergency managers who were attending in that room. And so I would say, updates on wind arrival time, what kind of observations have been seen, closer to where the tsunami started. And so those were really efficient ways to share down that information. And then the last one I've mentioned already is the Emergency Coordination Center conference calls. We have another technology that goes out by text alert, and this is through the Everbridge program. And this is where local individuals can sign up to get emergency alerts on their phone. And so the county emergency managers can send out more specific information to their local residents through this Everbridge text alerts. So that, if one community knows that they're going to have a larger impact, or the forecast are saying that they have a larger impact, they can let their people know. And there's a number of different ways that we also can alert the public during these events. Some communities have tsunami sirens, but we don't have a centralized coordinated tsunami siren program because the Oregon coast, you can't hear the sirens very far if it's a windy day, and it's almost always a windy day on the Oregon coast. But some communities have them. And we also have, different call down services. We get it out to the media as much as possible. And there's a lot of, peer-to-peer information sharing out there. Next slide. So when we're looking at the response to this, it's important to understand that in Oregon, we get two different types of tsunamis. We get the local tsunami from the Cascadia subduction zone earthquake, and we get distant tsunamis. And it seems like since I started working here, we've had a distant tsunami, or the possibility of a distant tsunami from an earthquake somewhere around the Pacific Basin almost every year. And this has given us a great opportunity to practice our response over time and evolve along with the technology. But some of our past distant tsunami events that we've had, for instance, the 1964 Alaska Good Friday earthquake and tsunami, that killed 4 people on the Oregon coast. And that event really sparked a lot of the development of tsunami response in Oregon. And then the 2011 Japan event, that was a very significant event. We were seeing between 2 and 3 meters of height when it reached Oregon. Luckily, it was a peak low tide when most of that surge was coming in. Otherwise, we probably would have seen inundation that day. We did not see much inundation that day, but we had millions of dollars worth of damages in several different ports and harbors on the south end of the coast. And then 2022, this was the volcano, the Hunga-Tonga volcano down in the South Pacific. And this really kind of opened our eyes that maybe we need to expand what kind of originating events we look at for possible tsunamis, because we did not know that a volcano in the South Pacific could cause a tsunami that reaches Oregon. And then, of course, the Kamchatka event this summer. So we do a lot of public education on the coast. We are constantly doing public outreach events, working with our local partners, giving them information to share. We started a couple of years ago a new preparedness program called Be 2 Weeks Ready, where we train local people to share this information out. For instance, if someone in the neighborhood wants to get their neighborhoods better prepared, they can get trained in the Be 2 Weeks Ready and hold that program. And because when we're looking at tsunami response in Oregon, really it's about managing behavior most of the time, because we're not dealing with the earthquake. We're only dealing with the much smaller waves from those distant tsunamis. And what we want to avoid is what we saw in 2011. People heard a tsunami was coming, and they tried to drive inland really quickly. And this was early March, and we had injury accidents, on the road because people were driving really fast. So we really keyed our education outreach to really promote the fact that we get 2 types of tsunamis, and it's 2 types of responses. If you feel the earthquake, that's Cascadia, and you don't wait for an alarm or an alert to get to high ground and you take as many people along with you as possible. But if you get a tsunami alert, that's really the good news, because you have at least 3.5 hours before our closest source could have a tsunami hitting our shores. And all of this response sits within sort of an ecosystem of making plans. I'm currently working on a volcano coordination plan right now. So we'll take that plan and we will exercise that plan this fall with a Three Sisters volcanoes scenario. That will be a recovery exercise. And then we do a lot of training around this. So when we have a response, that's the product and that's the outcome of this planning, this training, this exercise, this whole ecosystem that we have in emergency management, so that when these kinds of no-notice events happen, we can respond very quickly. Next slide. And that is my presentation. That is my email address. So feel free to reach out if you have any further questions or you want to talk more about Oregon tsunamis, earthquakes, volcanoes. I'm always happy to chat. Thank you.
Wonderful. Thank you so much. When we were initiating this initiative, GeoRisk Network, it was very clear for us that we are not only fascinated by the scientific aspect and the hazard and the modeling, but also we are all dedicated to reducing the risk. So I very much appreciate this multidisciplinary panel. I pass it to John to introduce our next speaker.
Thank you very much, Sahar. Yes, I would like to introduce our last speaker, Dr. Nicolas Pondard. He is a disaster management specialist. He's worked across academia, government, and private industry for many years. Currently, he designs risk reduction and risk financing strategies at the World Bank. He supports the development of risk transfer solutions in the Pacific, specifically for the insurance risk pool called PICRIC, or the Pacific Catastrophe Risk Insurance Company. And Nico has some very interesting information to share with us about how this catastrophe risk pool was triggered by this Kamchatka tsunami event. So Nico, over to you. Thank you.
Thank you so much, John. And I hope you can see my screen now. So yeah, I take that as a yes.
That's great.
So yeah, awesome. Thank you. Thanks everyone for the kind invitation. I would like to basically spend 5-10 minutes to show you how we've used the scientific information that has been discussed in this session to inform disaster risk financing, in particularly in the South Pacific, which are composed of mostly low and middle income countries. So to give you a little bit of context, here you go. So yeah, to give you a bit of context, this is a report that has been produced by the World Bank, and that shows the losses that can be expected from natural hazards globally all over the world. And this report is a bit old. It's been published in 2017, but it gives a good idea of the situation. Every year, natural hazards trigger more than $300 billion of damage across the world. That's the top figure you can see here. But if you look at the bottom figure, the same year, the record amount of humanitarian assistance that was provided to manage those natural hazards was only total $22 billion. So as you can see, there is a massive discrepancy between the impact of disasters and actually the finance that is available in order to respond to those disasters. And as a result, the population, particularly in low and middle income countries, have to face the disaster themselves. The losses fall down to the individuals. They lose their homes, they lose their lives, they lose their livelihood. And so we need to shift the paradigm from humanitarian assistance and I would say reactive response to proactive and anticipation activities. And for that reason, governments try to basically work together and find ways and mechanisms in order to be able to access to finance And this could be in the form of loans, this could be in the form of building reserves, this could be in the form of buying insurance. But all of that is very, very difficult to do, particularly when you're in low or middle income countries. If I show the next one. So for that reason, the Pacific Island countries have got together and they have decided to create a facility that is called the Pacific Catastrophe Risk Insurance Company. It is actually not an insurance company. It's a not-for-profit development facility. It has been established in 2016. And the idea is that basically Pacific Island countries would pool resources together and really trying to set up pre-arranged disaster risk financing and associated services to the Pacific region. It's an initiative that has been created by the World Bank initially, and now it is independent. The purpose of this facility is not to be able to cover all the losses that government would have to manage following a disaster, but the idea is really to be able to get access to rapid liquidity, rapid cash, following a major disaster in order to respond to the immediate relief and response activity. Should it be, clearing infrastructure? Could it be providing food and equipment, or basically medicine supplies to impacted populations? Okay, and so this helps government to support their budget, and they have more confidence that because they have very limited budget, if they get access to this finance, they can maybe be able and confident that they can basically disburse and try to respond to the disaster, as opposed to letting individuals dealing with the situation themselves. And so you have a list of the countries that here at the bottom. Okay, so one example of this mechanism, and I will show you how this connects to the science that has been discussed before in the next slide, is what we call parametric insurance. And this is very important. Parametric insurance is not your traditional insurance cover, the way you insure your home or the way you insure your car. Instead, it is something that looks at pre-agreed parameters. And those pre-agreed parameters could be the category of a tropical cyclone. It could be the level of ground shaking following an earthquake. And this information is available almost immediately after the event, within the next few days. And based on that parameter, you define a trigger. If that trigger is exceeded, then a payout is provided within a few days after the disaster, as opposed to traditional insurance, where generally you would need to check the damage, and the payout would be provided 6 months to 12 months after a disaster, which is far too late, obviously. Okay. So the benefit, as I said, is that it's very rapid, and timing is really the issue here when you face an emergency. And it also helps to cover basically assets that may not have been able to be covered using traditional financial mechanism. The limitation, however, as I said, is that it is not connected to the damage. And so you could get cases where maybe the trigger has not been met. For example, the tropical cyclone category was too low, but still triggered damage. But because the trigger was too low, no payout has been provided. And so you need to have robust science to try to minimize the situation. So how does that relate with what we've been discussing before? So as has been discussed before, the Kamchatka earthquake had consequences that were far-reaching and went far beyond the Russian peninsula. And so when the tsunami got triggered, the wave propagated to the South Pacific countries. And in particular, you can see here with the figure from NOAA that the wave was relatively severe in the Solomon Islands and in Samoa, here in the middle of that figure. And so the Solomon Islands was not part of the program at the time. They have joined since. However, the government of Samoa was part of the program. And the government of Samoa had agreed to receive up to $1 million from that pool. How could this be triggered? So in order to be, as I said, proactive and fast, we have designed a solution that was actually based on the Pacific Tsunami Warning Center threat messages. So instead of waiting to check if a damage actually occurred, which would have basically taken weeks, actually simply based on the threat warning, we could trigger payouts, and this enabled the government of Samoa to be confident that they would receive funds in order to support impacted population. And the way this is done, so based on the various threat messages from the Pacific Tsunami Warning Center, there are three types of messages. One is a warning of a wave below 1 meter. Another one is a warning of a wave between 1 to 3 meters. And another one is a wave of more than 3 meters. Based on those various levels, the government of Samoa received a share of basically the projected payout. In the case of that event, the warning was of a wave of 1 to 3 meters impacting the north of the coast of Samoa. As a result, within 10 days of the event, the government of Samoa received 30% of the fund that was pre-agreed. This corresponds to approximately $300,000, which of course can sound to be very small and very minimal, but actually does make a huge difference when it is provided at the right time. And so because it was given fairly quickly to the government of Samoa and they knew it was arriving, they've basically taken up on themselves to use some of their very limited budget to go clear the road and try to clean some debris and use that fund in order to do that. And this helped accelerating the relief and recovery effort. One last point I would like to make is that earlier it was discussed that, of course, the threat messages actually are sometimes inconsistent with the reality, and it was the case here, actually. The warning was of a wave of more than 1 meter. The actual wave at the coast was actually of 70 centimeters. So the threat warning was very conservative. In that case, for us, it's a good thing. And this is the reason we use the warnings, that because those warnings are designed for life safety, they tend to be more conservative. And so that means that the government tend to receive payouts more often than actually needed. So that's what we call a false positive. So so in that case, as I said, because we're not for-profit institution, this is a mechanism that works. So again, it's not a perfect solution, and those solutions actually exist also for earthquake, they exist for flood, they exist for tropical cyclones. It's far from being perfect, but it has the benefit of enabling the release of finances within a few days after an event, which is something that was not possible before, and hopefully makes an impact. So I'll stop there, and I'd be happy to answer any question. Thank you so much. And here you've got my contact details if you need to follow up. Thank you.
Wonderful. Thank you so much, Nico. It's also important to note that Nico is part of the task force, so he has been with us in the past few months in shaping the initiative. So I get instructions from Malaika that we are going to open for Q&A and go to spend a few more minutes. If you need to leave, we totally understand. We are at time. Am I understanding correctly? But we continue for a few more minutes. Many of the questions have been answered already on the chat. One question that I wanted to ask from all the speakers to make a comment are, you already shared some of the key lessons you have learned, very specific to your objective of the work related to this event. But you also showed beautifully how you benefit from upstream, other institutions, organizations that take care of the instrumentation or various aspects of data modeling related to this event, how you benefit upstream from the work of these other organizations in your own regions and internationally, and how you support others downstream who benefit from your work. If each of you make a quick comment of how in this specific event, what was your experience from that point of view? I just add that in today's world, I think it is really nice and beautiful to see what we have established in coordination and collaboration across the world. Who wants to start? Maybe we can go the way we started. Zoe, would you like to start?
Sure. Yeah, I totally echo what you're saying, that what we do is only possible through the kind of global collaboration and the interdisciplinary collaboration. So for us, I mean, we benefit from the Global Seismic Network, which is already a global collaboration, and that's kind of the backbone of how we detect and monitor seismicity globally. But in this case, one of the interesting parts of it was the regional strong motion center. So there is a really robust regional strong motion network in Kamchatka, but for political reasons, they're not as able to share that data. And so that was kind of a challenge for us. And that's always a little bit of a tricky part of the response for us is how and in how much detail we're able to acquire that data. And so, yeah, that was one piece of it that was kind of interesting.
Great. Thank you for sharing that. Who is next? Fabrizio or another?
Yes.
Yes, go ahead, please.
Just a short comment. Since I work in the Italian Tsunami Warning Center, and we anytime such a kind of earthquake like Kamchatka occur in the world, we use the experience from and what we learn from such a kind of events for our system that fortunately is in a smaller basin with not so frequent events, but this while from one side is a lucky situation, from the other side is the opposite, because we are not so prepared like the Pacific basin to such a kind of events. And so anytime we try to learn and to make efforts to become much more robust like system, not only like Italy, but also with the rest of the tsunami service provider in the Mediterranean, France, Turkey, Greece, and so the scope in the future, and we are working currently, is to become much more interoperable. And I'm lucky because I work in such a kind of system and group. So that's it from my side, my 5 cents.
Great. Thank you for sharing that. Ben, would you like to comment on?
Sure. I think I guess two or three bits here that I spoke a lot about the Tokyo Volcanic Ash Advisory Center, and that's one of nine of these centers around the world. And something that's wonderful about them and really, really neat is that most of the scientists making those observations are not trained volcano people or scientists. They are people with a remote sensing background or meteorology background who have been, I guess, asked to do this or learn about volcanoes. And so they're making these observations, keeping us aware of what's going on. And then they also pass let's say that you're in Tokyo and you just noticed that Klyuchevskoy made a really big eruption cloud, and it's moving along, and at a certain point they pass that cloud, gets responsibility passed to the next volcanic ash advisory center. In that case, it would go to Anchorage. And so there's this collaboration happening across countries around the world, among people who aren't even volcano scientists, and they're helping us monitor these volcanoes. And then the other part, and this gets to what Zoe was saying about the seismic networks, and there are certainly seismometers in Kamchatka, and the scientists at K-Vert and in Kamchatka use those to monitor these volcanoes. And unfortunately, we aren't always necessarily able to share those data because of political considerations, but those scientists do an amazing job and help constrain what's going on the ground. And as I think I said in the comments, the chat over here, having those on the ground observations are probably the most important, or one of the most important parts of monitoring a volcano, because I guess the two things you want to know is the ground shaking, because that might mean an eruption might be happening. And then the second thing is hopefully you have someone who can look at the volcano and say, yep, it's erupting. But if it's cloudy, then you can't really do that. So in that instance, then the ground-based networks come into play, and the scientists in Kamchatka and around the world do the best they can to try and make those networks happen to help everyone around the world.
Wonderful. Great. Thank you. Althea, would you like to make a comment about connections and collaboration?
Yeah, because earthquakes and tsunamis are a no-notice event. It's not like wildland fire or flooding or hurricanes that gives us days, if not weeks, of advance notice. It's really the relationships and the practicing and the exercising that we do ahead of time that really makes a difference, because when we do a tsunami response, it's time limited. The earthquake happens and then the tsunami is going to start arriving. So we have, that much time to get people to do what they're supposed to be doing. And that's why, working with the modelers, both deterministic and probabilistic, ahead of time, and having some of those things in our back pocket already. So if it's from here, we kind of expect that. If it's from there, we kind of expect that. And then just, learning from this event, even with Kamchatka, we learned a lot about how we can coordinate better with the National Tsunami Warning Center and with our local partners. So each of these events is a learning opportunity. And we were getting questions about volcanoes because there were active volcanoes in the area. So when these kind of events happen, it's not just earthquake, tsunami. It's a whole environment of questions and information that we need to share.
Wonderful, thank you. And in a sense, in your role, these connections at one side are with scientific organizations and technical organizations, and on the other side can go as far as entities dealing with the general public and directly with the general public. Wide diversity. Nico, please close it off with your comments.
Sure. Thanks. Just trying to add to all the great comments from the others. I mean, I want to say that obviously nothing at the World Bank or in the Creek facility that I've talked about would be possible without the collaboration of the scientific community, but then also, of course, private sector when it comes to the financing world and political institution. And in this particular tsunami, as I said, it was critical to be able to monitor the event in real time, and this basically required all the global data that was provided by NOAA, by USGS, by PTWC, and without this, we would be in the dark and we wouldn't be able to make a decision. And so here, particularly when it comes to the scientific community for us acts as an independent and a transparent provider of information, and it really helps to make all the stakeholders, agree, and particularly when it comes to the financial world, you have to be unbiased, and you have to basically have transparent rules so that donors, can be confident that they're going to trigger funding for beneficiaries, and the beneficiaries, will receive. And this needs to be transparent and understood by everyone. And none of that could be possible without the network of scientific data that's been provided. So I want to say thank you.
Wonderful. Huge thank you to all of these organizations. And to all of you, the speakers and the participants. I pass it to Malaika to close our session.
Yes, thank you, Sahar. And thank you so much to all the speakers. I felt like that was a great evolution of talks and information. And thanks so much for the kind of knowledge sharing and inspiration to bring us together. I did launch this poll. Please share if you'd like to comment on what you would like to see from this network. And do engage with us. We welcome any contributions and input. But a big thanks to the speakers. That was I think a perfect level, and I really enjoyed each one. I thought there was just amazing level of information and knowledge shared. So thank you, and appreciate the diversity from around the world. We'll seek to do something similar next time. I've seen a couple positive comments that this was well received. So I hope we can do it again. Not that I hope we have a massive cascading hazard event anytime soon, but there will always be fodder for discussion like this. So thank you, and please do connect on at our website at georisknet.org. Become a member, contribute. We welcome anyone's time and contributions, and join us in any way you can. Thanks so much.
Thank you.
Thank you. Bye.
Thank you.
Thank you.
Thanks. Bye-bye.
Thanks, everyone. Goodbye. Thanks.